little bit like, let's go with a small introduction. I really want to know you guys. I know it's late for introductions, but if everyone can, uh, if you want to turn on your mic and speak up one sentence about you, like what you do, what's your major, and like what do you expect. Like, let's leave the expected part out of this. We can take that next time. Just your name and what do you major in. That's what we can talk about. And I'll write up. Yeah, you can type it in the chat. And if someone wants to speak up, they can, or else you can write in the chat so that I will write your names, take your attendance, and I'll get to know you.
Hi, my name's Aditya. I'm a business management and data science student.
Okay, yeah. Aditya.
I'm Dev. I'm a data science major, second year.
Mm-hmm. I just want to write the names. Okay. Yep.
Hi, my name's Keaton. I'm a data science major and a business minor.
Data science, maybe. John is also a data science major. Are there two Johns in our class? In our lab specifically? There are two Johns? Yeah. Yeah, there are two, right? Yeah. And then we have Leo. Leo, what is Leo is majoring in data. So we have a lot of data science students. I mean, that's understood that this subject would be taken by DS students. It's like, wow. I don't know if this class is required for it isn't required. It isn't as a requirement. Yeah. Samantha is a DS student. Angelina, third DS student. No. DS student. Okay. Faces an informatics student. No computer science students take this course. Yeah.
Yes, that's what the data science minor takes course.
Yeah. Yeah, I got everyone's name. That's good. I think we don't have a lot of people in the lab because it's cold outside, like windy and everything. Maybe that's why people are not joining us in person, but that's okay. Start sharing my screen.
Should we do this in a notebook file or?
You can do it in a notebook. You can do anything, yeah. Both are fine, doesn't matter. Okay, I hope my screen is visible to. No, no, okay, sorry. Now,
Yeah.
yep, okay. So what do we have for today? Let's go to what's to. Let's see first. Let's see who came and who didn't. Not in the students. We have to go in the labs. Parker, was Parker here? No, right. Parker is not here. She, Shinjini. She's not here as well. John is here. Aditya is here. Roddy is here. Azam is not here, right? Angelina is here. No, Noah is not present, right? Yep. Will is here. Aman is not. Aman is not present. Okay.
It's an old picture.
Okay. Yeah. How do you spell your name? Like how do you spell it?
Nathaniel.
Nathaniel. Thank you. Because that's what I don't forget it. You are also a DS major, data science.
I'm actually weirdly enough, I'm a game design major. But
Wow.
Data science.
Nice.
So quite a bit different.
Oh, that's good. Dave is here. Leonardo is not. John is here. No
I
one
think
is
Leonardo's here.
Leonardo is here.
Leo.
Leo. Yeah, okay, Leo, yeah.
Yeah.
Makes sense. Grace is here, yeah. Info student. Keaton is here, yeah, data science. Gavin, again. You only have 2 or 3 students from different fields. I would remember you guys definitely.
I mean, I think it's harder when less people show up.
Yeah,
In person.
yeah.
Like match face.
Yeah, you don't understand who's who. Because this might be, I mean, I have a very older picture, so it's like 5 years back. Yeah, is not here. Samantha is here, and Joseph. We both are here. Makes sense. Thanks everyone for joining in. Let's go to the labs. What to do? We have lab 4 that we're going to do today. That is implementation of heap. I know you guys have gone through heap in lectures with Professor German, but I would say let's go through a refresher of what you guys learned in heap. Yep. Let's open a homework that is, yeah, AVL heap on paper. Let's take this as an example. And can I write? Is there any way I could be able to like?
I think this should be like a sidebar with this candidate data. Is that what you're trying to do?
I just want to write on the screen, just
Yeah.
like pencil. Is it not here? Yeah. Can you write in Zoom or can I can open
You
it?
should be able to. There's a way to annotate.
Yeah.
Zoom.
Let's search if we is it like only host can do the annotate? I can do.
I think it's usually just like there's options right so anybody can annotate, but usually it's oh there.
Whiteboard.
Usually there's just an option on the side where it's
Yeah.
I can make you host. Yeah, that might be it.
You can make me co-host. That is also the same thing, I think.
Oh, yeah. You do that or make it so everyone can annotate, but I don't know if you want to. I think I made you co-host. It should just be an option.
Yeah, it usually is over there. It says it is somewhere in here. Let's open a whiteboard. That is also fine. Yeah, let's do a whiteboard. So We are studying heap. And I hope everyone has the question opened in their computers, but let's for everyone's confirmation, let's write the insert digits over here. Where did the whiteboard go? Come on.
You can use Microsoft Teams as well.
Yeah, I could do that.
I think that's probably like.
Yeah. Let's do that. I just want to do a refreshing kind of thing on the heap so that everyone is a bit comfortable with. Paint, right?
Yeah. That's like pretty much just.
Yeah, I see. Select the card. Okay, that's fine. Heap. Does anyone know what is heap or what are the properties of heap? No. Anyone online wants to volunteer on this one? Properties of heap or what is a heap or how is it different from binary tree? How is a heap ADT different? Does anyone know heap ADT? What is the full form of ADT?
So like it keeps sorts, I don't know if it's necessarily numbers, but it's just like the input, like the nodes by
Mhm.
their binary form, so it,
Yeah, something like that.
yeah.
Something like that.
It always goes in order,
Mhm.
like how the nodes go down.
Yeah, yeah, it's a good answer. Yeah.
The different variables.
Yeah, I mean, that's a good answer. Actually, you got most of the points. But it's, if you think about very simply, what is a heap, then it's just another binary tree, but it's not a binary search tree. It's not BST. That's what the difference is between a heap and a binary search tree. So actually, when you let's say you do a binary search tree, a BST, and let's say you start with 10, where would the 3 go? This is 10, I'm sorry.
Those are normal BSC.
It's a BST. Where would the 3
it's
go?
gonna go to the left.
To the left. Mhm.
Then with the heat, would it normally swap? It would be 10.
Yeah, we'll get to that.
Yeah.
What he put to just like understanding the base and difference over here. We'll get to what you say. I mean, you are there. You're correct. But I want to ask people from online, where would let's say we are inserting 59. We are inserting 59 now. Where would it go? For a BST. We are talking about BST here. Oh yeah. Right of 10. Yeah, correct. So let's write 59 here. Where would a let's say just 9. Where would the 9 go? In a
The 9 would go to the left of 59. No, to the right of 3. Sorry.
to the right of the 3 here. Is this correct? Where you want 9 to be? Okay. Yeah. I mean, what you do here is you start inserting 9, you search here, 10 is bigger than that, you go left, 3 smaller than that, you go right, and you insert the 9 here. That's how you do it in a binary search tree, right? So let's say this is your binary search tree. But I can notice one thing, that this tree is not balanced. So what the difference between heap and a BST, heap ADT and a BST, is that heap trees are always balanced. That's what the major difference is. So if you do the same thing in heap, but let's not think about any order changing, swapping or anything. If you just think about inserting values without even like zero knowledge about what heap is. So if you really start with heap, then 10 would go here. And I think everyone has, not everyone, but most of the people, if they were present in the lecture, then they know what heap is and where would the, let's say this 359. Now, if it's in heap, where would the 9 go? And I'm not talking about any swapping or anything here.
Just go to the left of 3.
Left of 3. Yeah. Let's say we have something like 12 that would go here. Then here, then here. That's how it fills up from left to right. And that is how you would never find a unbalanced heap tree. You wouldn't have anywhere you wouldn't have a value that's missing. This you want to have 9 missing from here. You wouldn't have 59 missing from here. This always goes from, this fills up from left to right. So that is the reason. Here it would be 1. On the second level, it will be 2. On the third level, it will be 4, then 8, then 16. That's how this heap ADT trees would fill up. So do you guys notice a pattern here about something like 1, 2, 4, 8, 16? Where are we going with this? Let's, for example, I think professor also said this in the lecture, but I'm just refreshing here. So where would the 14th element go? Let's say 14th element. 14th element. Can I ask your name and your major? Is take an introduction for everyone. Thank you. And you are majoring in data science. Thank you. So yeah, where would the 14th element go? I had this question. Let's ask from the people online. I'm very bad with my handwriting then. Dave, you wanna go ahead and maybe let us know where the 14th element would be or what would be the process or anything that comes up.
Like the under 16 or the same row as 16.
No, I was just asking, let's forget about the rows here. Where would the 14th element, where would the exactly, where would I place the 14th element?
Like on the tree that you have over there?
Yeah, for example, this is the first element, this is the second, this is the third, fourth, fifth, then this is the sixth one, then this is the seventh one. Let's say there are like a lot of that here. Where would the 14th element go? How would I find it? Do I just
Not
keep
sh-
checking?
Yeah, I mean, you would just keep checking the numbers, right?
You just keep checking the numbers, and what if I have to find an element that is on, let's say the tree is full. Let's think that every element in here is full according to what heap requires. And let's say I want to find 103rd element. That is 103rd element I want to find in the tree. Where would that go?
It would be like at the bottom, like really low.
Mhm. Yeah, I mean it's true. But how would I find where the 103rd element would go is uh, I would just calculate the binary for that number, for that element.
Oh, yeah. Binary numbers.
Yeah, you wanna know the binary representation of the number, and that would show you where the number would be. So let's see for 14th first where that would go. For 14th, what is the binary representation for 14th? Can anyone tell me that? So let's make it a bit more easier. So first, we are calculating in base 2. So this is 1, this is 2, this is 4. I have no space. This is 4, this is 8. Do I have to write anything more here because we have a smaller element? Let's say I start from here. Let's say I start from 8. That is 8. This is 12. This is 14. That's 0. Is this a correct representation for 14? So how would I know how would I use this binary representation to actually know where the 14th element would be? Let's think there is 1, 2, 3, 4, 5, 6, and 7, 8. Okay, there are elements here. I left one here. Yep. So how would I know where this 1, 1, 1, 0 would go?
Yeah, there's 1 represent going right on the binary tree and 0 left. Sure.
I think yes. Yep.
Yeah, I mean,
You know, right?
yeah.
So how would you actually would you move from left to right or would you move from right to left for actually looking in the tree or going below?
Wouldn't it be, you start on left to go right, at least with those numbers?
Yeah. So this is 1. So this is the first element, you skip it. Then you go to, then this one. So you go to right, left, left. 1 is for left or 1 is for right?
1 is right, so it would just be right, right, right.
Right, right, and left.
I think so.
Here it would be for 14th element. One, two, three, four, 5, 6, 7, 8,
Maybe-
9, 10,
So
11.
even though it's, of course, it's like,
So this would be 14th.
okay. Yes.
So you were correct actually. This is 1, this is 1, and this is 0. So here your 14th element would be. This is where your 15th element would be. So I think everyone got a good idea about where, if you are actually looking for a particular location, where how would you find it? That's the basic, like very basic of heap. And so let's look at the lab 4, and that says that the development of heap ADT is presented in the 7 stages below. So let's look at the first stage. What is that? Basic data structure with smart display. So what does this do? It's like, I think we are inserting something in the tree. So this shows 1, end of the first is something written in the print statements there. Then we are inserting 3, then we're inserting 4, inserting 5. So this is what we learned here, right? We are not even doing anything. It's just simply adding elements, how the heap property works from left to right and making it as balanced as possible. So let's look at the code for the stage 1. And we start with this code, which is given. This is the given class that has this whole code written here. And let's open, yep. Let's open the Colab notebook. And what I would do is, first I would just, this is something that is given to you by the professor. So I would just do is paste it off and I would see what it is doing. So what I saw is the same thing that you saw in the output before. And what it is actually doing is just like this display function, the auxiliary function that is written over here. You don't have to like actually, if you want to understand how we are doing this, just designing how we are doing these linings, how it is going below. That's what this is about. If you want to understand this, you're welcome to, but I don't think you have to understand where are the spaces and where is this underscore going and everything. The logic for heap ADT is what we are here to understand. So, and if this question, for example, if this question is asked in exam, in your midterm exam, then we would give you this print function. So don't worry about what this print function is doing. Then what is different here? If we skip this, if we take this out, then what are the other things that are written here? This is an constructor. Everyone knows the init function in a Python code is a constructor. So we define key, right, and left here, the three things that we have defined here. And we are just displaying everything. This display function is getting called by the print statements or the object that you have created here, and you're just calling the function up. And what it is doing is just calling the display auxiliary function inside, and recursively it's just printing your inputs that you are given it. So what you gave here is you gave 1, it did print 1. Then you did a display. So what it did is it displayed the whole tree for you. Then you did given 3, so it insert 3 for you. Then you write 4, so it wrote 4 for you. But now you are actually writing it on the left. So C is your given 3. That's the third, that is 3 here. This is C. Now you are writing C dot left and given for 4. So this 4 is going here in your class, and it's actually printing this print function is actually making it print on the left side of your 3. So that is how this is working. Then C dot right of given 5, so that is how it's 3. The 5 on your right of 3 is how it is printing here. So it's just very basic. You don't have to actually understand properly what is happening here, because this is actually a very basic given function to you. Now what you have to understand is basic insert. The stage 2, we are moving to stage 2 now. So that is basic insert implementation, no percolation. So basic insert implementation is what we saw here. We are just inserting everything. We inserted 3, we inserted 59, 9, 12, and then a lot of numbers. That is what we are trying to do here. So stage 2 is just insert 99. So that would insert it over here. Then insert 98. It is inserting 98 on the right of 100. Then 97 is inserting on 90 here. 96 is getting inserted here. So that what you see common here is whatever we learned here, the basic property, the very basic property of heap is making a balanced binary tree. That's what it is doing. How it is doing it, let's look at that. So extend the code with this, the second part. This is what professor has given, and that is in a JPG, I guess a picture format. But I guess he also told you where you can get the code from. But what I feel is rather than just copy pasting the code, I think you should understand what actually the code is doing, because that would actually make you understand the concept of what heap is and how it is working in a step-by-step kind of a manner. Because if you see the whole program that is in stage 7 directly, you won't understand what is happening here. This is very confusing. So that is how you get to stage 7, by actually writing the code from stage 1 till stage 7. Let's look at the stage 2. And what did we do different here than the function that we wrote before? I think everything that is written here in your heap function, heap class, now we have defined a new class that is inheriting from the given class that is written over here. So you might get errors if you directly copy the code, and if you are importing the statements that are actually not needed here in your Python, in your Colab notebook. If you are actually using the Python file in your, let's say, Visual Studio, then you might have to import statements that were given in the code. But this is what we are defining. We are like defining the heap over here in a constructor. Then we have written a size function. So what this size function is doing is the display is inherited. Okay, so it is actually the display function from your given class is inherited here. And now we are writing the size function. Let's look at what the size function is and why do we need it. It's necessary to determine the new insert location. So let me open this on the side, or this is also fine. Like if you're thinking about 99, let's say insert 99. So how would you know where to insert 99? So for that, you have to know the size of your tree. So that is what this function is calculating it for you. So you look at the left side of that of your tree. So let's say you are here 100. Look at the left side of your tree. Sorry, look at the left side of the tree, nothing is there. You look on the right side of your tree, there's nothing here. So what you do is you return 1. That is the size of your tree. So inserting 100 would give you the size of 1. So if 1 is returned, so you did insert 100 here. You were inserting 98. Let's say you're inserting 98 here. The value is 98. And for that, first they calculate the size. So your size that came out from this function is 1, and it adds 1 here. It uses the binary representation of heap size to locate, like actually where to put your number. So this is calculating the binary format of the number that is mentioned here. So you are looking for a second element to insert. You have your first element. You're looking for a second element to insert in your tree. That is the reason every time we add 1 here, because the size would give you what is the current size of your tree. So for example, if you are on 10th element, let's say if you are here. So what is the size of this tree? Okay, people have answered. That's good. Can anyone tell me what is the size of the tree that I have just highlighted? One. Size means, okay, I thought professor did cover the size, but let's cover the size again. For example, this is your tree. Let's take this out. 100, 9, say 5, 3, and 2. So the size of your tree now is 1, 2, 3, 4, and 5. That is what the size of your tree is. This is calculating the amount of total numbers of values that are in your tree. The size of this tree is 5. That's what this is. So now can you tell me what is the size of this tree? Very simple. Size of tree is 6 here. Thank you. So 6 is your size. And if you are trying to insert one more element in there, where would that go? So this is your 6th element, right? First, second, third, fourth, fifth, and 6th. Your 7th element would go here, just on the right of 98. So how would this process actually work? That you are inserting, let's say 97, it's 95 here. Oh, it's 94 here. Let's think we're inserting 94 here. So how would the code understand to actually move down to the tree and actually insert your element where it is supposed to be according to the heap properties? So that is what the first step for that is, calculating the size of your tree. And that is what this function is doing. If the left is none and the right is none, you return 1. But that is not the case here, right? Let's say if left is none, so 100 left is not none, and right is also not none. You have values there. So this both conditions won't be true here, right? Sorry, this both, yeah. Is everyone agrees with me? I hope, yeah. I hope everyone agrees with me. And this is the else function, where it is actually saying that both left and right children exist. So this is the case where both of your right and left children exist. So what you do is first you add 1 to the right size and then to the left side, so that this would actually calculate the right size of your tree. And so this is the right side. Let's say 199 is the left side and 198 is your right side. So this would calculate 1 and 1, and then it would add 1 to that. So if you are looking at just this much tree, then the size is 3. And this would keep, it's a recursive function. So this would keep going on, and that is how it would calculate till here, till the 99, 97, 96, it would call this else function. But as soon as it comes at this 98, it only has one left. This would get called because your right is none and your left has one element. So that's what this would give you. So till now, your left size would have been, let's say 1, 2, 3, 4, 5, 6, or let's say 5, and the sixth element would get added here by this last line that I just highlighted. That's what gives you the size 6. And the size 6 plus 1 is 7th, and 7th element's binary format would be what? Let's say what would be the binary format for 7? For 7, 1, 2, and 4. This would get us the answer 1, 1, and 1 would be the binary format of your 7th element. So again, we go from left to right. So left to right is 1, 1, 1. So your element would be inserted. This is 1. This is again right 1. Again right. Oh, sorry. Okay, this is 100. This is right 98. That is 1. This is again a right 1. That is your last element. 94 would be inserted here, and that's what this shows. That is the reason we are actually calculating the binary format here. Then this last line, self.helper, is calling an helper function that is written over here. And what it is doing is it removes the first character or as the first one represents the root and passes the remaining to the helper. So it always removes the first character because that that this one is not going to make any difference in your output because that's where you start. So 1 and 1 is actually deciding where your element. Both ones are actually deciding where your element is going to go. That is the reason it is skipping the first one. For example, you get to this function now, helper function, that gets path and value. So if the path is 1 character long, time to add. So if path equal to 1, insert leaf as the right child. So let's say, let's take the same example that we are taking before. We are inserting 94, right? 94 gave us 1, 1, and 1. We are skipping the first one. So there we are left with 2 ones. So this would be your first one. And you would insert self-right heap value. So on the right of 100, you inserted 98. Then you won't go here because you don't have a 0. You go to else, and that says the next step. So you're looking for the next element in your path. So that is where this would go. Then if the next step is 0, that is not the case for us. So else self.right.helper would actually return the value and actually return the position where the value should go. That is this position. That's what this else condition would give you. Any confusions here? This is the first step. If everyone understands the first step and if everyone is with me till here, then we can move forward. Okay, I hope everyone understood the first step. So this did print the same thing as what I think there are different values inserted here and here. I think everyone knows what this for loop and displaying, this is like printing functions, inserting it and displaying. That's what it's doing. Nothing fancy here. So now we move to the third stage, and that is adding percolations to insert when and where needed. So now we are actually implementing the heap property of percolation. So that is jumping or swapping the values, anything that you might understand. So let's remove this or let's create a new one. Yep. For example, let's open what this is. We did insert 100 first. And now we are inserting 99. So for what we have learned till now, would 99 go here? Can anyone say yes from the chat? If whatever we have learned till now, would 99 be where it is right now or not? Yes or a no? Let's ask someone. Grace. You there?
Sorry, can you repeat the question?
Yeah, sure. So if whatever we have learned till now, till step 2, will 99 go on the left of 100 or not? As of for the heap properties that we have learned till now, we don't know anything about percolations. We don't know anything about swapping the values. Anything and everything that we have learned till now about this, would 99 be there or not?
Yeah, because we haven't done the swapping yet.
Yeah, sure. Thank you. So now comes into the picture the property of heap, that is swapping the smallest value up to the top. So anytime you see a heap tree, the first value, the root value on the top would be the smallest value. So 99 would swap, and this would give you 99 and 100 here. So that's what this also states, that this is where the swapping happened. Then if you insert 98, let's take this out. If I want to insert 98, where would that go? But now we are trying to insert 98 here. But this is wrong, because 98 is the smallest element in the tree, and it can swap. So you're swapping this over here, and the 99 goes here. So 98, 100, and 99. So does this tree looks like an heap ADT tree with the requirements that we have learned till now? Does this looks okay? Is it correct? I think it is correct. So that's what this stage 3 is trying to implement, and let's see what that does. So what have we made different in this part of the code, in the third stage of the code? So our size function is still the same, because anytime you calculate the size, you don't have to change anything. This is a generalized function. You don't have to do anything here. You just call this function and you get the size of the tree at that point. Then this insert function has something new here. And this is that this is a new line that is added to the insert function. So what is the new line? After we calculate the path, the binary path, and after we pass it to the helper function that actually gives you the position where your element should go. This is the, let's say, for example, let's say go to stage 2, and 94, while inserting 94, the helper function gave you the position here where it got inserted. After giving you the position, we are now calling a new function that is self.clean. What is this new function doing? What is the clean function here for? Let's see what the clean function is actually doing. And the helper function is still the same as before. Is for calculating the position where your element would go. That's nothing new in there. Then what is this new clean function actually doing? Let's separate it from the top. This is a new method which makes your smallest number bubbles up. So that is what we learned now, that your smallest number, for example, 98 here, should bubble up, and that should be over here. That's what this function is doing. So what we are checking first is, if your left side of the tree is not none, you call the left side of the tree with the clean method. So there's a recursive call happening here. If your right side of the tree is not none, you go to the, you again check to the right side of the tree with again recursive call in the clean function. And if the both sides, the left and the right, are none, you just pass. So what these two lines are doing here? Can anyone tell me what these two lines are actually doing here? Like logically, what this line would do in a tree, in a heap ADT tree. Like,
For relation, but like right here, just checking if like the children are empty, right? Like well, I guess checking to see if their children are empty.
yeah,
Yeah.
if they have a children or not. Yeah, and if they don't have any children, we just pass. Now we check the other condition, that is if the right side of the tree is none, that means we only have one child on the left. We check, for example, let's take an example for this so that it's better understood. Right is none. So let's say, let's take this 99 over here. If we are inserting 96 now, let's say it comes over here first and it checks that on your right side is none. Okay. Not this also. Let's take this example. If you are inserting 94 again and your right is none, what this would do is it would check if the self dot key, that is the key that you are trying to insert is 94 here, and self dot left dot key. So left of that, or let's say the key is what that you are on right now. Let's say 96, and on the left of that, it's checking if there is an element that is smaller than that. If it is smaller than that, we swap. That is what this elif function is doing. We swap if the left child is smaller. Why did we never check? Like now we are moving to else condition that is for two children. Why did we not write anything about the left equal to none?
Didn't you write anything about?
The left condition. We did take the right side of the tree into consideration. Why did we not take the consideration into the left side of the tree for a single point of element? Like let's say we are here at 99. Why did we not take into consideration the what would be the left side be? None. So for what are we talking about none? Is it like left side of the tree would be none? Left side of the tree would be none. So what I understood from this is if you have an heap ADT tree, you don't have to look at your left side because it would be filled up. You would always have to look if your right side is actually smaller or larger than you want to look if your right side is empty or not. That's what this concept is about. That is the reason we never mentioned the left equal to none condition here. So now we look at the final condition else, that is two children, and do you understand why? So that's what we discussed. For the two children, we see if the left side of the key, if the key is smaller than the left side and if the key is smaller than the right side, then you pass. That is that means that you are right now at incorrect position. The key that you are on is actually smaller than your left and right. That's what we wanted to do. So that is correct. So you pass. Elif self dot left dot key is less than the right dot key. So left key, let's say, I think we have to write an example for this or something so that people could understand what are we actually trying to do here. Let's say 100. And for this example, your left key is smaller than the right key. Let's say this is 98 and this is 99. So both are actually smaller than your element above. So how would you decide which element you want to swap it with? So that is where this line comes in. Your left key is less than your right key. That is the reason left key is the one that gets actually swapped. You guys know that this would be the one that would swap, but how would you explain the program to actually swap it? That is the reason this line is here for. Then you check if the left.
Yeah, just so you're finding the smallest.
Yeah, this is finding the smallest value in your tree. That's what this is about, nothing. Then you see if the left key is greater than the right key, then you swap it. Then you swap the left key with the right key. And if nothing, if every condition, I mean, you covered every condition till here. If there is nothing left, then you just pass. And that is the reason you covered everything. You have got to the end of the tree. That's it. That's what this clean function is for. And that is where you call after you get the position from your helper function, that is when you call the clean function. So I guess everyone had an idea about what we are doing. If not, if you guys have any doubt till now, let's discuss. Okay. Then we will move forward to the fourth stage. That is first part of remove top implemented no propagation. Does anyone know how the remove function or let's say delete works in a heap ADT tree? I know everyone has gone through delete function. Let's draw a tree here, something like 1, 7, 15, 19, 25. Let's say you don't have anything here. Let's remove this. Say we don't have anything here. How do you now? Let's say, I forgot to explain one concept, that is, if you ever come across an heap ADT, you would never be asked to actually delete a value from anywhere between the tree, because a heap ADT tree is always balanced. So your root element is the one that always gets out. So if you take 1 out of here, what would happen? What should happen according to heap properties? What should actually happen?
Whatever your last element.
So this is your last element. So this should go up.
Yeah, becomes the root and it just
Okay.
percolates again, right?
Yeah. So this should go up. So that says 25 should be here, and this is 7. This is 9. This is 15.
So you can only delete the root. Could you ever delete the last element?
No,
No. Or
just the root. Heap ADT tree has a property that says you can only delete the root for that.
I think it was like heaps are supposed to kind of represent like a queue data structure. Yeah.
Like you started in a single line. There are people behind you. So the one getting out first would be you, because there's already people behind you and you cannot turn back.
So yeah, the queue.
Something like it's not a proper line, but that's the concept. Yeah.
Yeah, that's what you mean. You could do it from the other end, but I guess it makes sense just.
Yeah. This is like there's no back doors. Once you come in, there's no you cannot get out. There's only one door that goes out of that exit. There is only one exit door. That is what this concept is about. So this would actually be your fourth stage. First part of remove top implemented, and let's see what this does. So first we insert 99 here. That is good with the property that we want an heap to follow, that is the smallest element stays on the top. Let's skip to inserting 93. So this is the tree that you have after you insert in 93. Now we start removing the top. So we took 93 out of this tree, out of this heap ADT. And what would that do actually? This 100, I mean, I cannot write it there. This 100 would actually go up there. That's what we discussed right now, that this 25 would go up there if your last element in your tree would swap with the root element, and this would just go out of the tree. So what happened here is 93 got out and the 100 got swapped. So this is why, this is the reason you got 100 here, 94 and 95, and the same thing that follows. But do you guys know that there are still small elements below this that could actually percolate to the top and like get defined by the whole heap property that we just learned? But this is not doing that, right? Your fourth stage is not doing the percolations, propagation, percolation, anything that you understand. But it's not actually doing anything. It's just removing from the top, and it's not abiding by the heap basic properties. So let's see how that stage 4 is implemented. So what did we did new than the stage 3 is our size function is still the same. Our insert function is again same. We're calling, but everyone should notice that we are calling the clean function here that we just learned in the stage 3. Your helper function is again the same. Now your clean function is also the same that we did in the insert in the stage 3 of adding percolations to insert that. This is your percolation function. Your clean function is your percolation function. Now the new code starts from here. That is remove top function that is written here. So this would first calculate the path, find the path to the last element. So you need to find the path to, let's say, side by side, keep it side by side. Let's say you want to find the path to 25. So how do you find it? You calculate the binary representation of that, and then you find the path. Then you get the value, pull the value from that node. You found the position. This is what position is it? 1, 2, 3, 4, 5, and 6. Your 25 is on 6th position. But you got to the 6th position. Now you want to know what number, what value is on 6th position that you get from this line by actually calling the helper remove function. This is also a new function that we would go through. Let's see what this helper remove function is doing. So pull the value from that node or navigates to the last node, and where is the other part? And returns its value. That's what this helper remove function is doing. So this got a self and a path. Path is getting passed from here. And if you see, it is again skipping the first element in your binary representation, because as we talked, that is of no use for us, because we know that we always start from the leaf, like not leaf, we'd always start from the root node. That is the reason you won't need your first binary representation. So we skip that. We move to, we check if the path is 1, we return the right key. We check if the path is 0, we return the left key. Else we check for the next step, and it's the same thing as you did in step 3. Where did we did that? Yeah, it's the same thing that is happening in the helper function, but this is where you're actually calling the left and the right side of your helper remove function. If the condition states 0, then you call the left side, and if the condition states 1, then you just call the right side of your tree for removing the element. This looks very similar to previous helper, right? This very similar, this previous helper. What are we doing now? Now we are placing the value in the root and cut the value from the tree. So now this step comes in where you push 25 to the top and you take 1 out of the top. This is where that step is happening. Now you traverse this. What this part of your code is doing, it traverses the binary part to reach the second last node, the parent of the last node. So P equal to self, last path is -1. So it calculates the path to your second last node. That is, your second last node is 1, 2, 3, 4, 5. And if you have switched this, then your second last node would be 15, I guess. Or wouldn't it be 15? What do you guys think? This is actually getting to the parent of the last node. So it is getting here. Your last node was 25. It was getting to the parent of the last node, that is 9. Or if you are here, then your parent for the last node would be 7. So that is what it is calculating, getting through the path, right, left, the same traversing logic that we wrote before as well. And then it returns the position where that is located. That's what this is. And that is the reason we are only, for the stage 4, we are only pushing the last value up to the top and nothing new is actually happening here. Now, if you understand that this is not a proper heap tree, because 7 has a very good possibility of switching with 25, and 25 can go here. So let's say 25, let's say 7 got out of here, 25 came here. 25 got out of here, 7 came here. But this 25 is still bigger than 15. This is where the elif condition comes in, where 15 and 19 are both less than 25, but we would look at only 15 because the condition that we have wrote that looks for only the smallest element from both. So the 15 would get swapped with 25. And here you would have 15. And here you would have 20. Sorry, here you would have 25. Now does your tree looks 7, 15, 9, 25, and 19. Now does your tree look like an heap ADT tree? Does it satisfy all the requirements that you have in your mind for heap ADT tree? Yes. Yep. Yeah, it does. I mean, yeah. So how do you do that? Writing the code. So adding propagations to remove top if, where, when needed is the conditions written over here. So let's say you were removing the top, that is 93. So you took 93 out, 100 came up here, 100 is bigger than 94, so they both got swapped. So 100 came here at 94, and 94 got swapped to the top. And 100 is actually bigger than 97. So 97 gets swapped again, and 100 comes here, and 97 is at the top. Now it looks like a proper heap ADT tree. That's what this is. 94 at the top, 97 in between, and 198 at the bottom. We never did anything with the right side of the tree because we were never concerned about that. The same thing goes with removing again 94. Then we removed 95 from the top. Then we removed 96, 97, and 98. And we kept going until like we lose the whole tree. So let's see how code does that. Was it this one? No. Yeah. So again, the same code, your size is same. Insert function, helper function, clean function. Clean function was from step 3. Remove top was from step 4. But let's see. There's a twist here. We're actually calling a new function, self.cleanRemove. We need to percolate the value down if needed. So before this, we also wrote a clean function here. Do you guys think that this would be very similar to what this clean function is and what the remove clean function that you want to write? Would this be very similar, or you don't think that?
I guess I'm thinking it should be similar. I don't
Yeah.
know why. I don't, for some reason, I feel like, I don't know why we have to rewrite it.
Yeah, why are we rewriting it, right?
Yeah.
Like you would know by step 7 if we really need to rewrite the functions or not.
Yeah.
If it is still not in there, then I would say that you should explore why are we rewriting it. If we don't need to rewrite, why, if we can take that We could reuse the code.
Yeah.
We don't have to write,
What situations will it like, will it change differently that number at the top?
for the removing.
Yeah,
For the removing, you wrote the function already, right? You already pushed in value to the top. That is, let's say you
Yeah.
push 25 to the top. So this is the condition that you are in.
How does clean work differently?
Yeah, that's what. Let's see how that works differently, or if it doesn't even work differently, if it's like really the same thing that is actually in there. So your clean remove function gets called. You see the left side and the right side, that is none. You pass. You see the right side, and if that is none, and then you check. So for example, uh, you see on the 9 and your right side is none, and left side is also none after 25 got up. But we don't have an example exactly here. But let's say you check on the right side and that is none. Then you check the key. If it's greater than the left side, so let's say this is the key, and if it's greater than the left side, we percolate it down. So we swap it down. In the clean function that we wrote before, we are percolating up. This is actually percolating larger values down. Then we wrote an else function. Again, the same concept goes behind. Why didn't we write the second elif function? This checks if the left key and the right key are present, and if they are less than the key that we are looking at, then we already are looking at the best heap tree possible. So you pass. Nothing needs to be pushed down here. If the left key and the right key, if the left key is less than the right key, so if 15, let's see this, we have this example. If 15 is less than 19, then who would you swap? Then you would swap the 15. This part is actually the same as what you wrote before. After you swap the 7 with 15, you call the self clean remove function. So you call this remove function again recursively, so that for example, you got sorted this value out, or you got sorted the first part of your value out. Your 7 is at the top, your other bigger value is at the bottom. But you cannot stop here. You also have to check there are values below that might be smaller than that, and you still need to percolate down. That is what this is checking. Now we check the else. This is the last function. The smallest is on the right side, so we swap with that. The smallest function 19. Let's say here we had 15. We swap 7 with that. So that's what the right key gets swapped over here with the key that you are actually at that position right now. And then we call the clean function here. We don't call the clean remove function. We'll call the clean function now, as we are looking at the right side of the tree, not the left side of the tree. Your left side of the tree condition got cleared out here, I guess. And now you're looking at the right side of the tree. So let's see what this is actually doing. We did remove the top. Let's say this is a tree. We did remove the top 21 out of it. 22 got swapped. 23 got swapped with 22. And that's why you got this tree. We removed 22. Again, the same concept goes behind this. Now, if you are removing 25, you're getting a string index out of range error. Why are we getting this error if you are trying to remove 25? That is the only element left in your tree. Why does it not say that now you don't have any values left, something like null or none value? Why doesn't it gives you an output? Why does it give you a string index out of range? Because as of now, we haven't provided any conditions to it to actually check if there is only one value. The base case, we only have the base case. We haven't written the base case. That should be the first thing that should be written, but we haven't written it. So now in the sixth step, we would write the base case of if we have only one value left, how would we go down to that?
We get an error like we're starting the tree without a base case and we just have one value.
If you only have one value, you would get an error.
Yeah.
But you started with inserting values and then you started removing it.
So
That is the reason you.
in the clean remove that we just made, right? For removing top. What would happen if that's the only thing we had and we pass through like a normal insertion instead?
if you pass normal insertion into this,
Yeah.
then
Like,
yeah.
what would the problem be cause? Would it swap things that could be swapped or?
then these two conditions that are mentioned here, the left looking at the very bottom of your left and very bottom of your right are the conditions that are not written in the clean remove function because we are actually percolating down.
Gotcha.
When you add a new element, what you do is your concept for adding a new element is you add a new element here and then you percolate up. And if you want to remove something, you did remove it and you did switch to the top, and now you want to percolate down because your the value that you switched might be bigger than what it should be. That is the reason it is not checking that two values here. Now we move to step 6, that is handling the request to remove the top of an empty heap. So let's see. Till here you got a tree by inserting values. Now you removed 93. You got this. You keep removing. And till here you got 100. 100 is your last element left in the tree. Now you try to remove the top value in the heap, that is 100. So what the heap becomes is there's nothing, no value left in the heap, and that is giving you none. So this is what we wanted in our 5th step, but that the base case was not written. So this step 6 would cover your base case. So let's see. As you can see, size function the same, insert, helper, clean, remove top. Remove top was from your step 5. Helper remove was also from your step 5. No, remove top was from your step 4. Then helper remove was also from your step 4. Clean remove was from your step 5 that we just saw and that we just wrote, and we discussed why that is mentioned here. Then we saw that we are getting the index out of range because we haven't written the base cases. So these are the two base cases that is actually getting checked over here. Remove from the top of the heap. If heap is none, you return none. This is the condition that you had to write at like very beginning, but you realized after a point of time that if you keep removing, it would show that the heap is the index out of range, right? So if the left is equal to right and that is equal to none, so you return none. Then again, if both of these conditions are not true, you just call the heap a remove top. You just recursively calling this function to check if there is values below that or not. And this is a display heap function that you already wrote before in, I guess you wrote this function in the stage 1 itself, your display function, the same one. If the heap is none, you print none, else you call the heap.display function that is recursively calling this function to actually print the values. We should probably do something similar with insert is what and comment added here. We did with remove when we keep like adding things in there, it was adding it. When we started removing it, then we realized that there's an issue here. So we wrote the base cases for the remove top. Now we should add something, we should probably do something for this insert function as well. So that is where your stage 7 comes up, where you're wrapping up with a very small change about the insert function base cases, and you're just testing it with random values, let's say minus plus, if it's like going where it should be or not. Yeah, so it's still the same. Two methods are not the part of the class heap. These two methods are like totally different from your class heap and class given. That is the reason that's what is stated here. Instead, they are at top. They are at top level. They should be at top level because these are the base cases that needs to be checked before even getting into the tree. Now you import random and you put random values in there from minus 50 to 50. Just taking my values from minus 50 to 50 and you're inserting values in there. Let's say this could change every time. I mean, like if you do it again, maybe this could change to something else. Yeah. This did took 23 first. then it took 31, then 17, the same heap property that you guys looked through. Now removing the top wouldn't require any random variables, right? Because we know that heap ADT is always works as in you get the first element, the root element out of the tree. That's how the heap works. So I guess this covers our lab 4. And I mean, I will show you where you would find the code, but I would still suggest that you understand what the code is actually doing rather than just like copy pasting it. This is where you find your first, I think professor showed you this. This is your first code that you got. And if you switch to here, that gave you the second stage of your code. And for submissions also, I guess for submissions also, we are taking 7 stages. We are taking S001 to S007, right? Or we are taking just the 7th stage.
I think we should just say, no, I'm pretty sure, but we could.
I'll ask professor and
Yeah.
we'll update on that.
Yeah.
So this is the second step. This is, let's say, the 4th step, your 4th stage. This is your 7th stage. Yep. This is where you are with your 7th stage, your final code, everything runs perfectly. This wraps up the lab 4, but I think if you guys have any questions, definitely we would be more than happy to help. If anyone has any questions, or we can move on with something new.
The homework, DST.
Mhm.
Like, just like you explained in class, we're able to do, like, after we delete something, we're able to do our own way if we want to find like the
Yeah,
furthest thing left on the right side.
Yeah. you could do your own way as well. Yeah, that's fine. Because VST doesn't have any something requirements or a specific order that it follows. For here, we had the binary path that we were following, but for
We have our own test cases in for our BSD.
for BST. Did you look at the code that was let's go through? I think that's a good idea. If no one has any doubt, then let's look at the implementation of BST. And for that, let's first look at what the BST question was. We were asked to insert 9, 2, 1, 10, 8, 3, 7, 4, 6, 5. Let's do that. And everyone knows this is the third or fourth time we are doing this. But yeah. I think professor has also given you a bit solution about this as well. Let's go to class notes. What's new? And this is what we wrote in class. So your homework 2, for that you can check this. Let's see what this is. It's a code. This is the code from homework 4. Okay. This is where you could actually that data structures.live San Francisco website. This is what that is.
I think it's the one below.
This one, yeah, that's a San Francisco. So let's do that. Let's do that. Yeah. So you had, let's open the question. Watch 2, homework 2, 9 to 10. Let's insert 9 here. I'll decrease the speed a bit so we know where things are going. But for inserting, I guess everyone is a bit clear about where things should go. 2, 1, then 10. Then would go on the right of 9, that's correct. And we insert 8. 8 should go on the left of 2. Yeah. Then 3. Where should 3 go? From 9, we go to 2, go to 3 is where 8. Should 3 be somewhere here? I don't know. Let's try. Yep, 3 is here. 7 goes. Where does 7 go? On 3 is right. Yep. Then where does 4 go? 4 goes on left of 7, I guess. Yep. Then comes 6. 6. This is what the San Francisco website states. And for inserting, I don't think we have to follow any order. It's just like the same thing that would be in everyone's mind. For removal, there is if you choose from left or if you choose from right, we'll see that as well. Now we are left with just one element, that is 5. We did insert 5. 5 would go on the left of 6. Yep. So this is your binary search tree. Now you delete 9, and now I will decrease the speed a bit to understand what is actually happening here. For deleting 9, you could choose from the left, and from the left, which element would you choose to actually replace 9?
Furthest right one.
Sorry,
The furthest right one from left, so where you can't go right.
for the side one from the left. So it's 5,
Well,
so it's 8,
yeah,
so it's somewhat right. 8, we'll choose 8. Yep, sure. Let's see what the San Francisco website does. We delete 9. It took 8 to the top, then it switched 3 with 8, and the tree below that remained the same. We pause it here, we take a step back. So 9 was here. We started checking. We checked 2, we checked 8. We take a step forward. We checked 8, and 8 is the one that we decided to swap. We take the 8 up, we took the 9 out. Take again a step forward. Your 8 now is gone because it is up there. So forget about this. So it switched to 3, and that is where this is where you are right now. Now, if you take again the root out, I think let's look at the code, what the code is doing. You could have also selected 10, and you could have calculated 10 up and 9 below, then just you could have got done with that.
yeah. So like when we're choosing like in our code, we have the choice of going right first or left first. We're saying what is the closest number? If you go right first, what is the closest number that's larger?
Yeah.
Left is, what is the closest number? That's
Closest
smaller?
number, yeah.
We always have to like. It's not either or, right? It's like both. So like if you don't have anything on the right, it becomes the left, right? It's the closest number, but it's smaller.
So
Well, like
do you
if
have an example for what you
So I just know like what happens if you're searching on the grid.
Yeah, well, if there's nothing on the right, you then have to be left. It's not like it doesn't get replaced, correct?
Yeah. If
So
you don't have
which
anything
case
right,
you have the right pieces for both. It just depends on which one you check first, right?
for the right, you don't have to, like, if you are choosing left side, you stick with that till the end of your program. That's it. You don't have to look at right.
Really? So it doesn't matter.
Yeah, it doesn't matter if the right side had very big value that was actually good to go up. That doesn't matter. Binary search tree, you have to choose left, you go left. You have to choose right, you go right. You don't change each and every step.
Well, not each and every step, but I mean, once one's empty.
You're saying if one of the subtrees is empty, could you go to the?
Like if there's no, if you're going right.
Uh-huh.
And 10 is empty, and there's nothing on the right, you then go left and find the closest value, but it's smaller than.
But you decided to go right and there was no value there, right? That's what you think. Then you select that now for the whole program that I would be doing, I would be switching to left side.
Well, but in class, I think he gave an example where like, then he swapped to the left. It felt like.
I didn't got the point. Like, for example, let's say 10 is not here. Let's say
So
this.
like when you see the program, you're only, you choose if you want.
Yeah,
the
you
closest value
choose.
higher or the closest value smaller. And if there's no closest value higher, it doesn't move, it doesn't change.
Yeah, that is kind of an edge case that could be imagined. Like if there is no,
Right.
there is no.
Like I said, in this case, if our program is checking right, and
Yep.
there is no 10.
So let's say 8. If you are taking 8 out right now,
Yeah.
and there is no value in here that is larger than 8. There is like nothing here that is bigger than 8. Let's see what happens. If we take 8 out, and we have slowed
I mean,
down.
this is gonna get 7, right? Because this checks left first.
Yeah, this side just take left first.
Yeah.
But if you go with the right at this point,
Yeah,
then you don't find anything closer. If you find 10 that is like closer to that, you just switch 10 to 8 and that's
yeah,
it.
and then after that, you move to 10, and you're checking right, there's nothing.
There's nothing on the right, so you have to, that is the situation that you have to look at the left side.
Okay, that's what I'm saying.
Yeah,
So,
that is like you are bound to look at left because you have nothing.
okay,
Yeah,
but is there ever a case you can get in a binary search tree where there's nothing on the left and everything's on the right? Too, right?
might be. Yeah, that might be.
Yeah,
Then you
and
definitely
then you
have to look at the right function.
So it doesn't matter which one, you have to write the code for both cases, it just depends on which one you put first, right?
Yeah,
That's all I was trying to.
makes sense. Yeah, I'm sorry, I didn't understand. No, you explained it. I just like with an example, it's better to understand
Yeah.
with an example. That's what I think.
It doesn't really matter which case you.
Yeah.
It's just, we have to put both
Yeah.
cases.
Or else I don't know if let's keep taking values out of this and let's see. Let's take 10 out of this and let's see what happens. That would be our condition. That would be our thought. Like what would happen if we take 10 out, right? Delete 10. So 10 is out. And it didn't do anything.
Yeah, because it's not.
There's nothing to look on the right side to actually percolate up, down, anything. There's nothing here. So now if you keep removing, let's say you started. So this was a question. Is it clear now? Did you got your answer?
I was just asking about
The code that you have to write.
yeah, well, I was just saying like,
Maybe you
Well,
won't
binary
have, if there
search
is
tree-
nothing on the right side, maybe you just don't do anything. You just take it out and that's your first element.
Binary search tree, whenever you delete something, it tries to replace it with the closest value.
Yeah, that's what the concept is saying, that it would
Yeah.
replace it with the closest value. But this, I feel that is this confusing a bit in the edge cases that we can thought about.
No matter you choose left or right, it's not like my binary search tree only replaces with the closest lower value. It'll check both higher and lower.
Lower sides.
Which one you want.
Yeah,
Yeah.
which one do you want to do first? That's what the
That's what I
question
was-
is. Yeah, makes sense. Okay, so we see the homework lab. Homework 4, yeah, homework 4, implementation of binary search tree. So this is our tree. Okay, what are we doing here? Taking the elements out. Trees above are random. Your task is to design a BST ADT, then use it to create BST step by step. So you insert, keep inserting values. This is your final tree until you never did a delete function.
So with this, we will of course write the code for it, and then do you want us to kind of like the picture here, just like insert a bunch of stuff and start deleting stuff, and then just check and make sure.
Yeah, checking to make sure where it's going. Yeah, that's what this is about. And there is actually an example or let's say a solution that is mentioned by the professor. If you go to class notes, if you go to what's new, you go to what we wrote on Fab 5, then your homework 4 is here. Your homework 4 is here. Your BST node is a function that is given to you, the same display function that we wrote for heap, the same display function. So this is a class. This is the given class that you just studied for the whole lab that is given to you, and now you have to write the BST. Let's take this. Let's take this here, and class nodes what's new homework 4. So you are trying to implement something like this, right? Let's see what the code does. So you're first looking for the largest value, and you look for the bst.write. If the right tree is none, let's see what this code is actually doing. The right tree is none, you return the key. Else you return the largest value from the right. This code calculates the largest value on the right side if your right side is actually none. If your right side is none, it returns the key, or else if your left side, so it's actually a left bias tree, right?
It's just recursively trying to find the.
Find the lowest value on the largest value on the left side. Yeah,
That's
that's
the largest value is gonna be the right most node for primary. search.
makes sense. Yeah, it's gonna be the right most in your binary search tree.
Once, then it goes right.
Right.
Find A.
It's gonna go, yeah,
So just recursively going down.
on the right path, because that is where you have a very great possibility of finding your largest value.
So as soon as there's nothing on the left.
That's the base case. So basically, when there's nothing on the right, you found the most right.
Yeah.
That there's no right child.
Yeah.
And then that's your largest value.
And then I guess if there's nothing on the left, the first right thing is on the right, right? Because you're going from.
Yeah. Then you start from right. That is where you start.
Yeah, you check, there is no left.
Yeah.
So I
Then
can
you-
right.
Then it is actually inheriting from the BST node class that you would have been already given. Again, the same definition, like writing the constructor for your BST tree. Insert function, you see the self key equal to value. If you find the value that you want to insert, you just return that value. If your key is less than your value, then you check if the right is none. If your key is less than the value. So let's say you are somewhere, let's say 30 is what is your value here? If you are looking at this tree, you're 50 and 30, and you want to insert 17 there. What is your value and what is your key? We can go to the BST node as well and see if we can get something from here. So key is assigned here, and we are not calling anything here. But we might have written some code in bst.py file at the bottom while calling. So BST 8. So 8 is our, let's open a different, so that we don't have to switching. So this is your BST node. And whenever you call BST node, your constructor is the one that first takes the value. So your key is what is passed here. So 8 is your key. And your insert function is trying to insert the values from the same 1972645. That's what is mentioned here as well in your BST on paper. 921. So these are a bit different. 92110 and this is 1972645. The concept is still the same. So you go insert the values in there. You are at the 8. You call the key as in 8. Then you consider this tree, this print statement. Then you display the tree. So you want to insert 8 in your tree that is already being generated. So what this 8 would do is, it would come here, and your key is equal to value. If you find 8 in your tree, then you return the tree directly. And if your 8 is less than the value, then you go to the, and if your right side is none, then you go to the, if your right side is none, then you go to the right side. If your right side is not none, then you go to the left side. Else, for the else condition, you see if the left side is none, then you insert it into the left side. And again, the else condition, if your left side is not none, if the left side has some value in it, you go to the left of that tree and you insert that value on the left side of the, yeah, going down the tree in the same position that you actually started. If you started left, go left to the right. That's what it's.
So basically, your child is now being called by the function, and that's kind of the parent child.
Yeah.
You're trying to see if those kids, if they're like children there, or if you can insert below them.
Hmm.
That makes sense.
So this is your find function that actually looks for value equal to key. If you find the value in your key that whether you are actually looking for, you return true that you found it. Then if your value is greater than the key, you get to the right side of the tree, and if that is none, you return false. And if your right side has any values, you go to the find function with your right side while checking again on the right side. That's how you go to the bottom. That's what the insert function was also doing. So that's what the same thing will be done here. Now the remove function. So the remove function might be a bit, let's take this out, it's confusing us. assumes that the value in this tree somewhere. So this function, if you are writing remove 3 or remove 5, then this function assumes that there is a 5 in your tree. If you are writing 5 and there is no 5 in your tree, then you might get I don't know, you might try copy this code and try if that actually.
You might just get an error. There's
Yeah.
an exception, maybe.
Yeah, something
I
like
guess you
that.
can make an exception, just, well, you'd have to do the whole find thing and then.
Yeah.
You would get an
Or you
error.
can write a base case if the value
Yeah.
is present, or then you get a print statement that please enter the value that is already in the tree to remove.
Yeah, with the base case though, when it checks that it's in the tree, would you just record all the inserts into like maybe a list and then you can check that against the base case and then you don't have to look for it every time?
I mean, yeah, you could make an array of the
Because
elements
as
that you have
go to
inserted.
find something, when you get an error as soon as it's
Yeah.
not there,
Yeah,
right?
you could write a simple for loop if it's there in your insert, if it's there in your present tree or not.
Yeah.
Something like that. And it would traverse through the whole loop. It would see if it's there, then it's okay, true, otherwise false, and you get an error. That's what this would do. It looks, if you find the value, then it looks at the right side of your tree, and if that is none, it returns the left side, that is the value that should be removed. If the self dot left, if your left side of the tree is none, it returns the right side of your tree, which again changes due to the recursive call that is actually again and again making the same recursive calls every time. Now, if this both conditions are not satisfied, you go to the third condition, that is else. You calculate the largest value on the left side, and you this temporary variable num, you just assign that num to the key, and your left side is actually calling the left side function. Again, it's going down left and actually recursively calling the remove function to see if you find the largest value in your left or not. And if your self dot key is less than value, it checks on the, if it recursively calls the right side of the remove function and goes below that. It keeps going
Yeah, it just keeps going down.
down, and if it finds the value, it returns the value. That's what this is doing, right?
Yep.
And at this last condition, if you have a self dot left remove function, again checking on the left side, bottom. If you find that, that's so the same thing you try to see on the left side, you don't find it, you see on the, again you go down to see the left side, you try it on from the top, you see from the right side, you find a value, returns the, so this is how it returns the largest value from your left or right side. So this is your last step, you get a value that should be removed, and if it gets removed, how it should be calculated. That's what this is. I mean, we can copy and see what this is doing. Okay, we have different examples. Let's see what this is.
So the interesting with the examples is he's actually not just like testing and figuring it out, he like just manually hand put in.
Yeah, he just manually hand putting it. That's fine. You can do that.
The draw function, why would you just draw it off?
For the draw function.
Well, I mean, there's a, like, we're giving.
For the display auxiliary
Yeah,
function.
display, yeah.
So
I mean, he could have just written out the tree, right, like insert stuff, and it would have printed that, right, but he wrote by hand.
I'm pretty sure uses a function.
we are using the function.
Oh, yes.
Yeah, we are using that same function that we wrote before.
Oh, no, that's just, he's just, commenting the output in the code. That's just.
Oh, okay.
That's the output.
Yeah, this is your output.
Yeah, that's just the output he put in
Yeah.
the file.
Gotcha, so you just copy paste it.
Yeah.
And it's just commented.
Gotcha.
So that if you run once or twice, you would like, we can take this out. If
There's a comment on Zoom.
oh, sorry. For the homework 4, do we use this code to create
Yeah,
a BST? Yeah, you can use this code to create a BST. But you should know what this code is actually doing. If some point in between we come and ask you that what did your code was actually doing, then you should be able to explain us that what it is actually doing.
also something like that might be on the midterm or something.
Yeah, this could be a midterm kind of a question as well. Yeah. I mean, I don't know, it's like guessing.
I mean, he's giving us examples of midterms, so.
Oh, he's gonna give you 6 examples. That's good.
Well, I don't know if he's gonna give us this one, but he's giving us like what past midterms look like, yeah. Are those, I'm guessing those are just taken in lecture or they? Yeah, in lecture.
So we don't have a BST node. That is the reason we got an error. So we have to copy that as well. BST node. Sorry. So this is good, but would we still get an error or would we won't get an error if I run this? That is my question. I literally said about this when we started the lecture.
Separate some of them into multiple different files.
No, this is I've copied. Literally, I've like copy pasted from bst.py and bstnode.py. That's what I copied.
I noticed there was like genres to with like the examples he gave us for the one we did.
Do you actually need this statement? Is my question.
The examples he gave us for lab, there's some of the earlier examples, like let's not finish it. Like one or two of the class names is a little different. So
Maybe yeah.
Yeah, you don't need, since it's in the same file, you don't need that.
Since actually it is in the same notebook, you don't have to write an import function. If you
And then
write
there's
import
second
function,
class, and you call the other class and like, you call, for the BST class, you're calling the subclass.
yeah, BST node.
Yeah.
And this is actually getting it from here. You don't have to write an import statement from this because this is in the same notebook.
That's basically the subclass.
So it's actually, for example, if you consider it is in the same
yeah.
Python file. So you don't have to actually.
Well, using a notebook, say you have another Python file, you can import that into a notebook still.
Yeah, you can do that. If you have two files, then you can import. But this is if you are following. I'm doing the same thing. So you don't have. Yeah, yep. So let's see what the remove function is doing here. We don't have a lot of time, but yeah, let's see what. Okay, you have this tree. Now you want to remove 15 from here. So 15 is here. So you take 15 out. And what is that? It's very big tree. I'm confused. So would this 18 take the place for 15, just that, and 23? So that's what it. You never touch the right side of the tree. So your right side condition checking didn't give you any output. So you tried looking at the left side. You push down to the left of 4. You came down here. You didn't find anything. You started looking at the right. You came at 12. Again left. You came to 11. Again right. You came to 23. Or if let's say we were looking for 15, right? You came to 15, and that is where you find it, and that's where your remove top function gets called, and that's where the 15 gets out, and then you again check for calculations, and that's where the 18 takes place for 15, and your 23 stays where it is. That's what this code is actually doing. I guess everyone got the idea of what we did with BST. So your homework 4 and lab 4 is covered. If you have any doubts, then definitely you should ask. For the homework 4, do we just have to copy paste the code and submit it to GitHub, or should we use the numbers from homework? I mean, I feel you should do.
I don't think they need to, because you know they have the random.
You don't have to, yeah.
Randomly generate.
Random variables, yeah. You don't have to do that, but if you want to see if actually what is happening with the code that you have written, or if it's like correct or not, I think you should try. If you want, you can write this 9 to 1, 10, 8, 3 values from homework 2. It's not a requirement, yeah. Okay, so that gets covered. So everyone is done. I will stop sharing. And if anyone doesn't have any doubt, then we can end this lab now. Thank you everyone for joining.